So, hi everybody. My name is Areg Adamyan. I am leading the Intel Go team, and besides contributing to the Intel Go upstream various optimizations and enabling for Intel, we also have a couple projects, and about one of which I'm going to tell you. This is about how to use Go differently, and you can see here we have different Gopher. So technical motivation. This is about the NFV, which stands for Network Function Virtualization. And you can think about network functions as any function that works on a wire, which processes packets, like switches, routers, and more complex ones like deep packet inspection, proxies. And for various reasons, for a long time, middle boxes, so-called middle boxes, were doing this functionality. Recently, community and industry is moving towards the VNFs, or virtualized network functions. Virtualized network functions are actually software written hardware appliance which put into the software and runs on a virtual machine. And we think that there are certain problems with VNFs and so-called ETCI framework that we are trying to solve. Currently, VNFs are very monolithic. They are actually virtual appliances converted from the hardware instead of doing network functions and doing the main function to process the packets. Significant part of VNFs now are about the plumbing into the ecosystem, plumbing into the infrastructure. And there are certain examples where plumbing VNFs into the communication service provider's network is really hard, and it's kind of art. There's a lack of a stable and unified APIs for VNFs control, both control and data plane. There are several challenges like accessing hardware accelerators from virtual machines, especially in the cloud environment, and there's no any cloud-friendly APIs for VNFs. So what we are trying to do is we are trying to bring microservice design concepts to designing VNFs. And for those purposes, we came up with the experimental framework, which we called YANFF, which stands for Yet Another Network Function Framework. And this framework built to create and develop performant cloud-native network functions. It is an open source project. Here is the link. You can go and check out it. It is based on the DPTK, but it provides much higher level abstractions than DPTK, and it's not a wrapper library for DPTK. It uses DPTK as a high-speed input-output engine. It's based on Go, apparently, and this is a carefully motivated choice due to productivity, performance, and concurrency we get from Go. And we program network functions here as application programs and not as a virtual machines. And the benefits that we get are quite straightforward. We easily leverage any hardware capabilities, like new instructions in Intel processors, like cache allocation techniques, direct access to DPTK, quick assist technology that we recently produced. It significantly 10 times reduced the efforts to develop the network function, and expands developer base, and actually we provide similar performance with C. So this is how it stands in the ecosystem. There's DPTK underneath, there are applications, and we came up with less is more, as you know. So we came up with two very powerful abstractions, and there are only two abstractions that you manage, the flow and packet. And you build processing graph using these flow functions and chaining them together. So we can do like receiver, handler, sender. And there are several predefined possibilities of adding user processing inside the packet. So we have built-in predefined functions for parsing packet, checking ACL rules, etc. One of the most important parts is that network function round to completion. So chain runs on a single process. We have a nice scheduler which allows you to also scale based on the incoming flow rate. There's zero copy between network functions, so we don't copy packets. And there is a flexible incoming flow handling. Sources can be anything. So it can be network, Ethernet, memory buffer, remote procedure call, doesn't matter. So this is the graph showing the basic components. On the left part are the flow functions. We have receive, send, stop. We can merge flows, we can split flows, we can partition flows based on some periodicity. We can separate flows based on some user-defined function. We can handle flows and packets inside one flow without separation based on the handle functions. There are two main notions, flow and packet, you can see here. And let's go further to show how it works. So this is an example. This is simple L3 rule-based forwarding. So we just initialize system on a 16 core, then we get rules to be passed from a configuration file. Then we create input flow on the port 0. Then we set output flows based on the split function, which is you can see on the bottom of the screen. And it splits the flows to the 5 outgoing flows, and that's it. And then we do system start. So this is the same example, which is called performance demonstrator from DPDK. It has pretty much about 2,000 lines of code. We have only 23. So what about the performance? The performance is written here. So this is preliminary results. But starting from 256 byte packets, we are on the line rate. So we can process all incoming packets. It comes for a cost of for sure. So we use 2 more cores on a box than DPDK does, but we produce the same performance as DPDK on a box. So this is about how we chain virtual network functions. So here you can see that there's the uncontroller producing rules, which you then feed to virtual switch like OVS, and then packets come inside OVS. It decides where to go, and it goes up to the virtual machine stack, up and down. That's etc. So what we do, we create this notion called network forwarding graph, and all the network functions works on that network forwarding graph and do not copy packets at all. So they just work on the same graph and utilize 0 copy. Then another point is the notion how to deploy it and how to use it in an existing cloud and existing infrastructure. This is done using our notion of cloud boundary node. It's actually what it does. It classifies the traffic according to the policy and forward it to the network functions after encapsulating to one of the transport of our choice. And similar on the reverse path. Here you can see the overall architecture. So the Ethernet networks come up to the boundary nodes. Then we can repack it to different transport, including Ethernet, memory buffer, files, remote procedure calls, doesn't matter. And forward it to the network functions, which can chain together in any cloud platform. It can be one node, it can be several nodes, or they work under the network, our YANFF scheduler, which actually interacts with any cloud orchestrator. For example, Kubernetes can it be. And this is the overall picture that I wanted to present, and I encourage you to go and check out the YANFF framework, try it, ask questions, and contribute it. Thanks.